This lesson is on the geometric area under curves. So we're going to look at the integral from a to b of f of x dx. What does that mean? Well, we're going to define that as the area under the curve y equals f of x above the x-axis in the case that f of x is positive on the interval from a to b. So the question is, how do we find that area? And this lesson is going to focus on rules of geometry that enable us to do that. So here our example is the integral from 1 to 4 of the function 5, y equals 5. That's a horizontal line. So I have a horizontal line at 5. I'm interested in the area under the curve as x ranges from 1 to 4. So here's our y equals 5. X is ranging from 1 to 4. What is this area? That's what this notation represents, at least in terms of our early definitions. Well, this is a rectangle. Finding the area of a rectangle is not going to be difficult. The length of the rectangle, 1, 2, 3, 4, 5, here. The width of the rectangle, 1, 2, 3, here. So the area of the rectangle is length times width, 5 times 3, or 15. So this notation, which we read as the integral from 1 to 4 of 5 dx, is going to equal 15. Now I want to check that with Wolfram Alpha, so I'll show you the notation that's used. We say integrate 5 dx, comma, x equals 1 dot dot 4. And you'll see what Wolfram Alpha gives us. It gives us the value. The answer indeed is 15, as well as a visual representation. So from 1 to 4 with a height of 5, we can see that the area under that curve will indeed be 15. Our next example is the integral from 2 to 4 of 3x minus 5. So 3x minus 5 is a line, not a horizontal line, but a line. We're interested in the area under the curve as x ranges from 2 to 4. So 3x minus 5, 3 times 2 is 6, 6 minus 5 is 1, y value is 1, 3 times 4 is 12, 12 minus 5 is 7, y value is 7. So here's our line, y equals 3x minus 5, interested in the area under the curve as x ranges from 2 to 4. So this thing is a trapezoid, but to make things simpler, I'm going to think of it as a rectangle down here and a triangle up here. We're going to add those two areas together to find the area under the curve. So again, here's the rectangle, there's the triangle. What's the area of this rectangle? Length is 2, height is 1. The area of this rectangle is 2 times 1, or just 2. Now I've got to find the area of this triangle. Base is 2, height is 1, 2, 3, 4, 5, 6. Again, starting at this blue line, triangle, 1, 2, 3, 4, 5, 6. So if you remember, the area of a triangle is 1/2 base times height. So base is 2, height is 6. Area is 1/2, 2 times 6. The area of that triangle is 6. We're interested in the total area. So if this area is 6 and the rectangular area is 2, you would say that our total area here is 6 plus 2. So the integral from 2 to 4 of 3x minus 5 is 6 plus 2, or is 8. So let's go ahead and check that with Wolfram Alpha. So our command is going to be to integrate 3x minus 5 dx. As x goes from 2 to 4, as we see. Wolfram Alpha gives us the answer here of 8, and then also shows us a visual representation, starting at x equals 2, ending at x equals 4 under this line. We get our answer of 8. So we've done two lines, a horizontal line and a non-horizontal line, an oblique line. Our next example will be a portion of a circle. So we have the integral from -5 to 5 of the square root of 25 minus x squared dx. So what does that look like? Well, that's a semicircle with a radius of 5. Now, this is the area we want. There's our graph. Y is root 25 minus x squared. Integrated as we go from -5 to 5. So the area of a circle is pi r squared, but I don't have an entire circle. I have a semicircle, half of a circle. So the area of a half a circle, semicircle, is a half of pi r squared. My radius here is 5. So it'll be a half of pi times 5 squared. That's 25 pi over 2. So we believe that's our integral from -5 to 5 of root 25 minus x squared dx. We believe that that's going to lead to a solution of 25 pi over 2. Now, let's check that with Wolfram Alpha. So again, our command is going to be to integrate square root 25 minus x squared dx. So here's the syntax I use. Integrate square root sqrt, parentheses 25 minus x squared, parentheses dx, comma, x goes from -5 to 5, and you'll see what Wolfram gives us. Gives us an answer of 25 pi over 2, which is what we thought it was, or approximately 39.27. So that's the area under the curve, the area of that half circle. Okay, next I want to approximate. So we're looking at the area under the curve. The curve I want here is 9 minus x squared. Integral from -3 to 3 of 9 minus x squared. What is that area going to be? Again, under the curve above the x-axis is how we're perceiving this. Well, I'm going to have to do my best to approximate this. So if I'm looking at it, 1, 2, 3, 4, 5, 6, 7, 8, and a little bit more. I don't know, 8.5, 9, something like that. So let's just kind of make our lives easier. Let's realize we're going to approximate a little too high. I'm going to say that this stack, 1, 2, 3, 4, 5, 6, 7, 8, 9, is close to 9, and this one is close to 9. Although clearly we're overshooting. We're saying it's a little more than we think it is. So, but that's my approximation. It's somewhere around 9. Now, the next stack, what is this? 1, 2, 3, 4, 5, and then these two pieces. That's about 6, 7 again. I think I'm going to overshoot this, but I'm going to approximate it. 1, 2, 3, 4, 5, 6, 7. Again, a little bit less than 7, but I'll go ahead. And we'll call that stack 7 and this stack 7 as well. 1, 2, 3, 4, 5, 6, 7, thereabouts. And then this last piece, what do we have here? We have these 4 or 5 pieces added together. What did I say they were approximately? So that was about 3. This is close to 1. This is close to 2. Add those together, fairly close to 3. Again, I think I'm overly generous here. So I think my actual answer will be a little bit less than this. But we're just trying to get some kind of a visual approximation for the integral, the area under the curve, from -3 to 3 of 9 minus x squared. So adding all those together, 10 and 9, 19 and 19, 38. So I believe my total area is somewhere in the neighborhood of 38, but probably a little bit less than that, based on how I approximated. So I'm going to again feed this to Wolfram Alpha and see what we get. So how are we going to do that? We're going to take integrate parentheses 9 minus x squared dx as x ranges from -3 to 3. What does Wolfram Alpha give me? Gives me 36. Again, I thought my approximation was a little bit too high, but, you know, I'm not that far off. 38 is my approximation. 36 was the actual number, so I'm in the ballpark. So I'm doing a reasonably good job of approximating that just by counting squares to get a feel for how this behaves. Now, all of our examples so far have been positive functions. They've never dipped below the x-axis. But let's take a look at what happens when they do. So this time I'm taking a look at the integral from -3 to 5 of 2x dx. So here is our graph. 2 times 5 is 10, 2 times -3 is -6, 2 times 0 is 0. So we want to find the area under the curve, but what does that mean? Well, this part is what it's always meant, the area under the curve here. But over here, it's below the curve. This is f of x times dx. So the height times the width. If the height is negative, height times width has to be negative. This is perceived as negative. So this portion of the area will count as positive area. This will count as negative area. So I will label it accordingly. So if we're above the x-axis, we consider the area positive. If we're below the x-axis, we consider it negative. And the total area will be to sum those up. So these are both triangles, so relatively easy for us to determine their area. So area of a triangle is 1/2 base times height. The base of this, 1, 2, 3, 4, 5. Height of this looks like it's 10. So the area of that triangle, the big triangle on the positive side, is 1/2 of 5 times 10, which is 25. So this then is perceived as positive 25. Over on this side, we're going to perceive it as negative. Now, the width is 3, 1, 2, 3. The length, 1, 2, 3, 4, 5, 6, or height is 6. So again, area is 1/2 base times height. Base is 3, height is 6, regarding our triangle. So 1/2 of 3 times 6 is just 9. But since it's below the x-axis, we're going to consider this a negative 9. So area up here is positive 25. Area down there is negative 9. But I'm interested in the integral from negative 3 to 5 of 2x dx. What is that going to require me to do? Add these two things together. 25 plus negative 9 will be 16. So we believe the integral from negative 3 to 5 of 2x dx is 16. Now again, I want to check that using Wolfram Alpha. So I will plug that in and see what we get. So my command will be integrate 2x dx, x equals negative 3 to 5. So there's the syntax that I use on Wolfram Alpha. And then we'll see what kind of result it gives me. You see we get 16, which is what we thought we would get. It also gives us a representation. Notice the positive area Wolfram puts in blue, the negative area Wolfram puts in red, interestingly enough. Let's do another approximation one. We want to look at the area under the curve. And this time I want to approximate the integral from 0 to pi of sine x dx. And I want to just get an approximation, a rough approximation of what that area is going to be. Now, sine x is always above the x-axis on the integral from 0 to pi. Notice pi about 3.14. I'm choosing to scale my graph this way because it's relatively easy to determine the areas. So I have 1, 2, 3 relatively large sections I should add in one very, very small piece. And I want to approximate the area under the curve to get a feel for what this is going to be. Well, this first piece, the width is 1, and this is awfully close to a rectangle or a square, 1 by 1. So it's a little short of this, but I'm going to go ahead and I'm going to say the area of this piece is about 1. Now, over here, I said that's about a half, because notice if I draw the diagonal here, that's about half the area, and this is a 1 by 1 square. Same thing here if I draw the diagonal here. This is a 1 by 1 square, so that area is about a half. But notice I undershot this thing a little bit. So I said, since I undershot this thing a little bit, and I can't really be sure if I undershot or overshot here, I'm going to call this little tiny piece beyond 3, between 3 and 3.14, basically negligible, about 0. So I'm going to add those three together to trying to eyeball this. 1, a half, a half. I'm going to say that this is pretty close to 2. So total area is 2. My integral from 0 to pi of sine x dx is 2. Now, is that what I get if I use Wolfram Alpha? So let me go ahead and plug that in. We'll say integrate sine x dx as x ranges from 0 to pi. What does it give me? Wow! Our approximation is exactly correct. Now, don't expect that to happen too often, as it didn't with our first example when we had 38 and 36. But it just so happens that I counterbalanced well. I overshot some, I undershot some, to go ahead and get a perfect approximation. Now I want to keep that in mind as I do a follow-up. So this time we're going to look at the integral from 0 to 2 pi of sine x dx. Now, what happens there? It's above the x-axis and then it's below the x-axis. Now what we said is this portion is perceived as positive and this portion is perceived as negative. But, you know, even if I hadn't done the approximation, I bet you could guess what that total is going to be. Because of symmetry, it looks like these two parts are exactly the same. So whatever here is positive, whatever is here is negative. So if I would add them together, it should be 0. Now, as it turns out, we know this integral from 0 to pi is 2. We just did that. Wolfram Alpha gave us an answer, not approximately 2, but was exactly 2. So based on symmetry, this graph is exactly the same. It's just below the x-axis. So this area also has to be 2. But since it is under the x-axis, we consider that to be negative 2. So then what is my total area going to be? Total area is 2 plus negative 2. Total area is going to be 0. Now let's again check that with Wolfram Alpha. So if we feed that in, what do we get? Integrate sine x dx as x ranges from 0 to 2 pi. Wolfram Alpha gives us an answer of 0. That's great. That's what we thought it was going to be. From 0 to pi here, again, 3.14 pi. It's blue. That's positive. From pi to 2 pi, it's red or pink. These two things cancel each other out, and my total area is 0. Now, what really are we dealing with here? What does this mean? So And we'll talk about this more when we do Riemann sums in our next lesson. But the integral from a to b of f of x dx is the sum, approximately, of the f of x's times change in x. And if f of x is negative, f of x times the change in x will be negative. That's the area under the curve that is below the x-axis. So that's going to be something for us to think about. But let's take a look at a visual of how this would work. So if this is a and this is b, the change in x is here. And I take, in this case, it looks like I'm using the left-hand endpoint to approximate what's happening. So I take a value of the function, which in this case is the left-hand endpoint, times the change in x. That gives me this rectangle plus this rectangle plus this rectangle, etc. So the sum of the height times the width gives me approximation for the area under the curve. Now, how does the approximation become better? It becomes better as the change in x shrinks to 0. As the change in x shrinks to 0, we're going to get a better and better approximation as we go. In the textbook, you'll see discussions on lower sums and upper sums. That's a formal way of doing this. Let's take a quick look at examples that follow this. So what I have here is a Desmos app. I have the function f of x is a half x squared. 2 squared is 4, half of 4 is 2. We can see how that's behaving in our picture. And right now I am dealing with 4 rectangles. So I've got this one, which is here. This one is here. This one is here. This one is here. So I'm using 4 different rectangles to approximate that. Let me see what we're dealing with. So the approximation on this is 2.203125. Now it can get better if I increase the number of rectangles that I'm using. Now we're going to go to 6, and we're at 1.9375. So notice the change in x is shrinking. The change in x is now to a half. If I go to n equals 12, notice I have many more rectangles. The change in x, the width is 3. There's 12 rectangles. The change in x now is 3/12. And I get 1.703125 as my approximation. Just keep doubling it and see what we get. 24, 1.597, 48, 1.5478, 96, 1.52, 200, 1.51, 2000, 1.501. And you see that it's probably heading towards what? Probably heading towards 1.5. Now, our idea here, back now just to 4. So 2.2 is a pretty bad approximation if you saw that it was heading towards 1.5. But notice how these are all overshooting. That's too big. So we can see from our picture that whatever we're using here, our approximation is indeed too big. But our actual value is going to be the limit as that change in x goes to 0, or the limit as the number of rectangles goes to infinity. That's going to go ahead and give us an approximation, an actual value for the area under the curve, an actual value for that integral. And we will talk about that when we do our formal discussion on the Riemann sum. And that will conclude this lesson.